This is the assignment 601.3 Work Energy Theorem problem set. And we're going to work through it starting with number one. Number one says, the net work done by the sum of all forces acting on a system equals. This is a definition, and your net work is equal to your change in kinetic energy. This is the work energy theorem. Question 2. A person and a bicycle have a combined mass of 78.8 kilograms. Let's go ahead and start by labeling some things. So we have a mass of 78.8 kilograms, and they are moving 10 meters per second. So velocity, 10 meters per second. How much kinetic energy does the system have? Okay, so KE again is 1/2 mv squared. So all we're going to do is 1/2 our mass, 78.8, times our velocity, 10 squared. Okay, so half of 78.8 times 100, because 10 squared, of course, is 100, gives me this, 3940, and again, it is going to be in units of joules. If the person pedals enough to do 1,590 joules of work, how much kinetic energy will the system have now? So this is the amount of kinetic energy that the system has initially. It's talking about a situation where we do work and we're adding more energy to that system. Okay, so that total energy that we have afterwards should be the sum of this initial energy plus the additional energy added by the pedaling, the 1,590. That should give us the total after the work is done. Okay, so that work is being done to increase the total kinetic energy of the system. So plus 1590, and that gives us a new kinetic energy of 5330, and again, still in units of joules. So this is my initial, and this is my new KE final, is 5530 joules. What is the new velocity of the system? So whenever they do this pedaling, it's causing the kinetic energy to increase, which means it's also causing them to get faster. That's the point of pedaling. Okay, and so we can actually solve for the new velocity because we know that this kinetic energy is still equal to 1/2 mv squared. Okay, which means it's still equal to 1/2 the mass, which is 78.8, times that velocity squared. So we're going to set that equal to this 5530. Half of 78.8 is 39.4. We're going to divide both sides by 39.4. That's going to isolate v squared. Again, this is not going to give us our answer. It's going to give us v squared. But v squared is going to be equal to 140.355 equals v squared. And of course, we want to take the square root of both sides. I have the whole value here rather than the rounded one. When I take the square root of that, I get 11.847 or 0.85 if I want to round it to 2 decimals, meters per second. And it should be faster than it was before, which it is. They were moving at 10, now it's 11.85, so it's almost 12. Question 3 says, a block of mass 3 kilograms slides along a horizontal surface that has negligible friction except for one section as shown above. The block arrives at the rough section with a speed of 5 meters per second and leaves it 0.5 seconds later with a speed of 3 meters per second. What is the magnitude of the work done by the frictional force exerted on the block by the rough section of the surface? So, we're going to write an energy transfer equation here. We have our initial energy plus any work done by the system. Okay, this is where our net work is going to go in the equation, is going to equal our final energy at the end. Okay, and the last question, we added energy in because we had pedaling on a bicycle to make it larger. In this question, we have a situation where we have work that's taking energy out of the system with friction. But this initial energy that we have, initially this block has kinetic energy because it's in motion. So that initial energy is KE. To that, we're going to add that net work. In this case, that's going to be the work done by friction. Okay, and that's going to give us a final energy. And we know that it's still moving at the end, so we still have KE at the end. This is just our initial, this is our final. Okay, so again, we're going to substitute in KE is 1/2 mv squared. In this case, it's our initial velocity squared, plus that work, again, that net work here is just the work done by friction, okay, equals KE final, again, 1/2 m times final velocity squared. So now we are at the point where we can go ahead and substitute in, and we should be able to get from here to solve for the magnitude of the work done by friction. That's what we're going to be solving for at the end of this. So let's plug in 1/2, the mass is 3, the initial velocity is 5, the mass is still 3 at the end. The final velocity at the end is 3. So this is going to become 1.5 times 25 plus the work done by friction equals 1.5 times 9. So let's go ahead and figure out what 1.5 times 25 is. That's 37.5. And then 1.5 times 9. We need to solve for this, so we're going to go ahead and isolate this by subtracting. These are currently being added, so we're going to subtract 37.5 from both sides. That's going to isolate our variable, and 13.5 minus 37.5 is going to give us our work done by friction, which is equal to -24 joules. So that is how much work friction did, which means it's also how much energy the friction removed from the system. We lost 24 joules of kinetic energy. The question, however, only wants the magnitude. So you'll notice none of these answers have a negative sign in front of them, and that's okay. But this is the magnitude of the work done by that frictional force is 24 joules. Number 4. Christian pushes a 13-kilogram box from rest along a horizontal surface until it reaches a speed of 2.96 meters per second. What is the work done on the box? Okay, so again, let's go ahead and think about this situation. We're going to start with a picture. So we have this initial state and we have a final state. Okay, initially this box is at rest. Okay, its mass is 13 kilograms. That's not going to change. Okay, but at the end, this box now is moving, and it's now moving with a final velocity of 2.96 meters per second. Okay, and so obviously what happened here is we have work being done because Christian is pushing this box, so plus work. So this initial state plus work done gives us a final state. Again, I'm just writing out an energy transfer equation, but I'm starting with a picture. But my initial energy plus any work that I do, any net work done on the system, doesn't have to be work I do, okay, is equal to the final energy of the system. That's our energy transfer equation. We just need to identify what form or forms of energy are present. So initially, I don't have any energy here. It's not moving. So my initial energy is 0. Okay, work done on this system, again, that's going to be the work from that push. There's no other work mentioned. There's no friction here that's mentioned. So it's just that. Okay, but you can leave it as net work if you want, but that's just going to be the work done on the box is going to be this right here. And then that final energy is kinetic because we have motion here. Again, the equation for kinetic energy, we can substitute in 1/2 mv squared. and that energy that it has is going to be due to the push it received. So the work that was done on the box will equal the kinetic energy it has at the end. This is the work energy theorem. Okay, so we don't know the work, that's what we're trying to find, but we do know the mass. It's 13 kilograms, and we know that it is moving with a velocity of 2.96 meters per second at the end. So that work is going to be equal to 1/2 mv squared. Okay, so let's go ahead and put this in our calculator. 0.5 times 13 times 2.96 squared. And that should be the work done. 56.95. Work is in units of joules. This is question number 5. It says, a 215 kilogram bobsled is pushed from rest along a horizontal surface by 2 athletes until it reaches a speed of 9.4 meters per second. Write the energy transfer equation for this scenario. Again, our energy transfer equations pretty much always look like this. We have our initial energy plus any work that is done equals our final energy. But we need to be more specific. What form of energy do we have? Well, initially it's at rest, so that's 0. But we do have work because it gets pushed. And that work is going to be where this final energy comes from. At the end, it's moving, so we have kinetic energy. So our energy transfer equation is this. Now, you're not going to see the 0 in there. It's just going to be work equals KE. What is the kinetic energy of the bobsled at this speed? Okay, so again, it wants to know what this KE is at the end, and again, KE is 1/2 mv squared, so we can solve for its kinetic energy by simply using that KE equation. So 1/2, its mass is 215, its velocity is 9.4. We're going to square that according to the equation. So 9.4 squared times 215, half of that, and we get 9,498.7 joules. So that would be its kinetic energy, 98.7 joules. What is the work done to accelerate it? Again, this KE that we just found is equal to the work. That's what this equation says. Work equals KE. So this is equal to KE, but it's also equal to work. I don't have to do another calculation. It's the exact same number that I just found. If the athletes push with a force of 235 newtons, what distance was the sled pushed to get up to speed? Okay, again, work, although it's equal to this value, work is also equal to force times distance. So I know the work, and I have a force now. So we're going to substitute in 9498.7 equals the force 235 times that distance. So if I want to solve for D, we're going to divide both sides by 235. And that's going to give us our distance that had to been pushed is 40.42 meters. Question 6. A book is sliding across the floor. It comes to rest after traveling 1.2 meters due to a friction force of 25 newtons. Write the energy transfer equation. Again, all energy transfer equations have the same basic structure. Our initial energy plus the net work done on the system is equal to the final energy. In this particular situation, we're dealing with a scenario where our initial energy is kinetic energy. We have work done by friction, and we don't have any final energy, 0, because it says it comes to a rest. Okay, and so the energy transfer equation here, okay, is going to be look like this. You can also rewrite it like this: KE initial equals that negative work done by friction, if you want to rearrange the equation. Okay, and so I think that's how they have it here, is that our KE that we start with initially is equal to, and it's really the negative work that we have at the end. You can see that here whenever I move that over here. All right, so what is the work done by friction to make the book come to a stop? So again, that work that's done by friction will be equal to the kinetic energy, or the magnitudes will be equal. And so if I figure out the initial kinetic energy, I can find that. Or the other way we can find work done by friction is force times displacement. And those are actually the pieces of information we have this time. So our work done by friction is equal to the frictional force, which is 25 newtons, and again, technically it's negative 25, times the displacement is 1.7. And so we're going to multiply our force, 25 or negative 25 times 1.7, which is the displacement, to get the work done as negative 42.5. And again, joules is our unit. And if this is how much work is done by friction to stop that book, then that is also the same magnitude of kinetic energy we started with. That means we started with 42.5 joules of kinetic energy, and all of it was lost due to friction. So that's the work is the change in that energy, the negative 42.5. But these will have the same magnitude, again, according to the equation that we wrote up here. All right, if the book has a mass of 9.4 kilograms, it's a really big book, what was the initial velocity of the book? Okay, so again, I know the kinetic energy initially is 42.5. And I know that kinetic energy is equal to 1/2 mv squared. I know the mass now is 9.4, and we can solve for the velocity. Okay, so half of 9.4, 9.4 divided by 2, okay, is 4.7, and we're going to divide both sides by 4.7. That's going to cancel that. It's going to leave us v squared. 42.5 divided by that 4.7 is going to give us v squared equals 9.04255. Again, I need to take the square root because we don't want v squared, we want v. And again, that's the unrounded value. When I round it, 3.01 meters per second. Question 7. Question 7 says, a 0.24 kilogram car is moving at 3.34 meters per second. When it rolls over the rug, it leaves the rug at 1 meter per second. How much work did the rug do on the car? So again, write the energy transfer equation first. That car had initial energy, there was work done on it, and now we have a final energy at the end. Okay, that initial energy, it was moving, so we had this initial kinetic energy plus the work done by the rug equals, and this is really going to be friction, is what that is, equals that final energy. It's still moving at the end, so we still have kinetic energy at the end. Again, KE, we don't have those values, rather we have things like mass and velocity, so we're going to need to substitute in the equation 1/2 mv squared plus that work done by the rug equals 1/2 mv squared. Okay, so now we can plug in. 1/2, the mass of the car is 0.24. The initial velocity was 3.34. And the final velocity is 1. All right. So this right here is 1.34, I'm rounding it a little bit, plus that work done by the rug equals that. Again, if I want to solve for this, I need to get it by itself, so we're going to subtract 1.34 from both sides. And we're going to get the work done by the rug is equal to negative 1.22 joules. And again, I have rounded that a little bit. Looks like that. Okay, but how much work? It will be a negative amount because the rug has caused the loss of energy of the car. Okay, so it's removed energy from the system. Negative 1.22 when I round that. All right, if the coefficient of friction, mu, is 0.18, how far does the car move across the rug? Again, we know that work is equal to not just this energy transfer equation here, but work is also equal to force times displacement. So we can find the displacement if we have the force. Okay, and we have the work. We have the work, we need the force. The force here, again, ultimately is due to friction between the rug and the car. And so when we look at the forces acting on this car, we know that we have Fn, we know that we have Fg, we know that those are equal and opposite, and we know that we have the force of friction. So my free body diagram would look something like this. I can calculate what this force of friction is. Again, its force of friction is mu times Fn. And they gave us mu in the question. So we just need to get Fn, and then we can find Ff, and then we can find what the question is asking for. Again, Fn is equal to Fg. These are equal and opposite. So we're going to find Fg. We're going to take our mass, 0.24. We're going to multiply it by gravity, 9.8. That's going to give us our weight of the car, 2.352. And then we're going to multiply that, because this is also Fn, it's both of these. Multiply it by mu. Mu in the question, 0.18. And so this is our force of friction. It's a pretty small number. Okay, but our force of friction is equal to negative 0.42336 newtons. Okay, and that force is the net force. And so that force is also what's causing work to be done by the rug. So work is equal to force times displacement. We know work is negative 1.22. We know the force exerted by the rug is negative 0.42336. We can figure out how far that thing will roll while this work is being done. And to do that, we are going to divide both sides by negative 0.42336. That's going to cancel this. That's going to give us delta x. Okay, so we're going to get our, I'm going to use the unrounded values on my calculator. And it gives us delta x equals 2.88 meters. How long was the car on the rug? Okay, well now we have delta x. We have an initial velocity and a final velocity. VI was 3.34, VF was 1. Again, those are in the question. And so we have information that we can use with our kinematic equations in order for us to find this. There's probably other, I'm trying to look and see. Yeah, we can also use the equation from last unit, F times T equals M times delta V. Either of those is going to work. I'm going to go ahead and use a kinematic equation, but again, there's more than one way to do this. So I'm going to take my delta x, my 2.88, and I'm going to set it equal to VF plus VI divided by 2 times T. This is one of my kinematic equations. So VF is 1, VI is 3.34 divided by 2 times T. So let's go ahead and do this. 1 plus 3.34 divided by 2 gives us this, 2.17 T, and on this side it's 2.88. Divide both sides by 2.17. And we get a time. And again, I'm using the unrounded values on my calculator. So my time is 1.33 seconds. All right, question number 8 says, examine the force displacement graph below. If a 5 kilogram object originally moving with a velocity of 2.6 meters per second is originally moving with that velocity, and then experiences the force shown in the graph as it moves from 0 to 30 meters. What is its kinetic energy after it travels that distance? So again, with the force displacement graph, we can find work, because work is force times displacement, which means work is equal to the area of this graph. Okay, and we're only looking at from 0 to 30, which actually is the whole graph, and so we need to find the area of the whole thing. So we're going to separate this into two regular shapes. The rectangle for the first 20 meters. So let's go ahead and do that. Length times width. For the first part, we're going to have 20 times 100. And then we're going to add to that the triangle. Again, that's going to be 1/2 base times height. The base from 20 to 30 is 10. The height is 100. Okay, so 1/2 of 10 is 5. 5 times 100, of course, is 500, plus 20 times 100. And so we're going to add those together. It's going to be 2,000 plus 500. Sorry, let me write it out. Is equal to 2,500 joules. So that's the amount of work that is represented by this graph. Okay, so we have this object that's initially moving. So let's write an energy transfer equation. Initial energy plus work equals final energy. Okay, so our initial energy is kinetic. We have a moving object, and then we have work done on that object, and then we have at the end kinetic energy afterward. Okay, and this is what it wants to know, is what is its kinetic energy at the end. Okay, we just found the work a minute ago, so we just need to get the KE here. Again, KE, we don't know the initial, but we do know that kinetic energy is equal to 1/2 mv squared, plus the work, I'm going to go ahead and put the 2,500 in here, equals KE at the end. Okay, so 1/2, the mass is 5, it's in the question. The initial velocity is 2.6. According to the equation, that needs to be squared, plus the work done adds even more energy to this system, 2,500 joules, equals the final energy it has at the end, which of course means it's going to be moving faster. Half of 5 times 2.6 squared, so 2.5 times 2.6 squared is 16.9 plus 2,500. It gives us this, 2516.9 equals our final kinetic energy. And again, this will be in joules. 2516.9. Last question on the assignment, 601.3. Says a 0.55 kilogram hockey puck slides across the ice. Its initial velocity is 12.5 meters per second after being struck, and it slides over an 11.2 meter stretch of ice with a frictional force of 2.27 newtons. What is the final velocity of the puck? So again, energy transfer equation. There's an initial energy of this puck, there's work done on this puck, and that's going to result in the final energy it has at the end. The energy it has initially is kinetic energy. The work that's being done on the puck here is work done by friction, because it's talking about after it's been hit. And so after it's been hit, it slows down a little bit because it goes over a frictional surface, and it's still moving at the end with kinetic energy. Okay, it's just moving a little bit slower. Again, we don't have the values for kinetic energy, so we need to substitute in the variables for KE. KE is equal to 1/2 mv squared, plus that work done by friction equals 1/2 mv squared at the end. Okay, so substituting in 1/2, the mass is 0.55. The initial velocity of the puck is 12.5 meters per second. We got to square that, plus the work done by friction. Again, work done by friction, work in general is force times displacement. Okay, and so here it tells us the force and the displacement. It tells us the frictional force is 2.27 newtons. You need to remember that's negative. Friction doesn't add energy, it takes it away. Negative 2.27 newtons times the displacement, 11.2, equals 1/2, again the mass is still the same, 0.55 v squared. Okay, so we have a lot of numbers here. Let's go ahead and solve for what we can. Half of 0.55 times 12.5 squared. This whole bit right here is 42.97 plus negative 2.27 times 11.2. Oops, I typed that wrong. 2.27 times 11.2 is negative 25.424 equals 0.275 v squared. So let's go ahead and add these over here. And I'm going to add the full values in my calculator rather than the rounded ones on my paper, just in case it makes a difference. This is 17.54475 equals 0.275 v squared. Divide both sides by 0.275 and then take the square root because that's v squared. We need v. And that gives us a final velocity, here it is, of 7.99 meters per second. How much energy is dissipated from the system due to friction? So we know that we've lost energy, and that's what that dissipated energy is, because we were initially moving 12.5 meters per second and now we're only moving 7.99 meters per second. This is asking us basically what the change in our kinetic energy is, because that change in kinetic energy, or that work done by friction, is equal to the energy that has been dissipated from the system. That work removed the energy, and therefore that energy is no longer usable. It has been dissipated. We actually already solved for it though. This right here, when we solved for the work done by friction, again, work done by friction is force times displacement. That is the energy that's been dissipated from the system. And that number was 25.424. It's right there. Okay, you could, if you wanted to, go back in and solve for the initial and final kinetic energies and then find the difference. But we already did it. That work done by friction is equal to the energy dissipated. Now, when it asks for work done by friction, the answer is a negative number, negative 25.424. But if I ask you for energy that has been dissipated, how much energy is dissipated, you don't report it as a negative number. You say this is how much is dissipated, and you give the magnitude of that answer. So I'm just reporting it as 25.424 joules. All right, that was the last question in the assignment 601.3. If you have any questions about this, any further questions about this, please make sure that you ask your teacher during class.